Welcome to today's deep dive. Usually when you think about a college syllabus, there's um, there's an expectation of human flexibility, right?
Yeah, absolutely. It usually operates almost like a negotiation.
Exactly. Like you miss a deadline, you send an email with, a polite excuse, maybe a bit of contrition, and the professor grants you a tiny bit of wiggle room.
Right. I mean, that's just the social contract of being human.
Yeah, but step into the world of computer information systems and you hit an absolute wall.
Oh, yeah, a brick wall.
Suddenly, we are looking at an instructional landscape that is, well, it's as rigid as a silicon wafer.
That's a great way to put it.
So today we're digging into a stack of sources, specifically a fall 2024 college syllabus for Introduction to Computer Information Systems. It's CIS41 at San Jose City College.
Yeah, taught by instructor Clem Lundy.
Right, and we've paired that with excerpts from the course's foundational textbooks like Discovering Computers and Microsoft Office 2013.
Which is such a fascinating stack of materials to look at together.
It really is. Because the mission of this deep dive isn't to just recap a reading list for you. We are exploring the collision between how computers actually process information at a physical level
Right.
and how humans have to, forcibly adapt their own behavior just to interact with them.
And honestly, the syllabus itself is the perfect entry point for that collision.
Really sets the tone.
It does. Instructor Clem Lundy, he doesn't just hand out a list of reading assignments. He issues what is basically an instruction manual for how to think like a machine.
Yeah.
And, looking at his background, it makes perfect sense. I mean, he's a former U.S. Air Force Master Electronics Technician.
Right, with all those heavy tech certifications too.
Exactly. Certifications spanning Microsoft Systems Engineering to the Cisco Network Architecture. His teaching philosophy is literally stamped right at the top of his profile.
Oh, the quote, yeah.
Chance favors a prepared mind.
Yeah, which is intense for a syllabus, but
Yeah.
I mean,
But think about it. A machine cannot improvise, right? It can't handle chance. It only understands what you have meticulously prepared it to understand.
okay, let's unpack this.
Oh.
Because he applies that absolute literalism directly to his students.
Oh, he absolutely does.
The course is built on 40 specific tasks within a learning management system, usually Canvas. And the formatting rules are just severe.
Severe is the right word.
Every single assignment must be submitted in what he explicitly calls a database-ready format. He, strips the human element out completely.
Right, because it forces the students to become essentially data entry nodes.
Yeah, exactly.
If you consider the sheer volume of assignments generated by a full roster of students, a professor could easily just be buried in information overload.
Oh, for sure. Hundreds of files a week.
Right, so Lundy solves this by demanding machine-like syntax.
And the required syntax is just wild. Like when creating an email account for the class,
Yeah.
a student cannot use their everyday personal address.
No Yahoo or Gmail they already have.
Right. They are required to generate a new one using a very specific string. It has to be CIS41 underscore, their 6-digit student ID at the domain,
Very specific.
and it gets better. For a PDF report, the file must be named with the 6-digit ID, a dash, the letters CHP, and the 2-digit chapter number, .pdf.
And if they mess that up,
Oh, if a student attaches the right homework but uses an email address that lacks that underscore, or, if they decide to be polite and type, "Hi, Mr. Lundy, here's my assignment," in the body of the email, they get 0 points.
yep, the system just rejects it.
0 points for saying hi.
But if we connect this to the bigger picture, that strictness is actually a real-world simulation of database management.
Oh, interesting. How so?
Well, later in the semester, these same students use Microsoft Access to build lookup lists and data validation rules, right?
Right. Access is heavy in this course.
Exactly. And a validation rule in a database is basically a locked door. If you try to input, say, a phone number into a field that only accepts dates, the database doesn't try to figure out what you meant.
Right. It doesn't say, "Oh, I know what they were going for."
Exactly. It just throws an error. And Lundy manually grades everything in the final week of class.
Wait, all of it. In the final week.
Yes. So by enforcing this database-ready format, he ensures he can run automated queries to sort, filter, and process hundreds of files instantly.
Oh, wow. So he is essentially programming his students to be peripheral devices feeding clean data into his mainframe,
That is exactly what he's doing.
which, makes you wonder how the literal machine on the desk is actually processing those strict inputs. We're constantly typing these commands, assuming the machine just sort of knows what an email or a PDF is.
We really take that for granted.
We do. But at a foundational level, A computer is just a box of rocks and metal that we've tricked into thinking by pushing electricity through it.
I love that description. And that is where the Universal Computer Model, or the UCM, becomes so essential to understand.
Right, the syllabus brings this up early on.
Yeah, the syllabus uses the UCM to map out how human intent actually translates into electrical action. It breaks down into three distinct codependent layers.
Started with the physical stuff.
Right, the foundation is the hardware layer. These are the physical components: the motherboard, the RAM chips, the hard disks, the copper traces.
But hardware is pretty useless on its own. I mean, if you just plug a motherboard into a wall, it doesn't do anything but get warm.
Exactly, it just sits there.
There has to be a translator, which is the firmware layer, right?
Yes. Firmware is sort of the unsung hero of the UCM. It's software that is permanently etched into the hardware itself.
Oh, like the BIOS.
Yes, the BIOS is the most common example, the basic input-output system. When you hit the power button, the BIOS wakes up first.
It's like the computer's morning routine.
Basically, yeah. It sends electrical pulses out to check if the RAM is there, if the keyboard is connected, if the hard drive is actually spinning.
Checking all its limbs to make sure everything's attached.
Right. It establishes the basic physical reality of the machine before handing control over to the final layer.
Which is the software layer, specifically the operating system.
Right. Windows, Mac OS, Linux.
Yeah, the OS takes over, and that is where the human user finally interacts. Like, we click a mouse in the software layer, the firmware translates that into a physical location on the hardware, and the hardware executes the electrical change.
And all of this orchestration happens on the motherboard, which is essentially the physical map of the computer.
Right.
It routes all these electrical signals directly to the CPU, the central processing unit.
The brain of the whole operation.
Exactly. The microprocessor is this little silicon wafer packed with billions of microscopic transistors acting as tiny electrical switches.
Billions. It's so hard to conceptualize.
It really is. And the texts highlight three critical metrics that determine how fast that CPU can flip those switches. You have clock speed, word size, and core count.
Okay, I want to push back on how these are marketed to people, though. Because you look at a laptop box at the store and see gigahertz and 64-bit, and most consumers, we just lump it all together as speed.
Oh, totally. It's just a marketing buzzword to most people.
Right. But mechanically, they're entirely different bottlenecks. I'll test an analogy out here.
Let's hear it.
Let's say the CPU is a chef working in a kitchen. Clock speed is the physical rhythm of the chef's knife.
Okay, I like that.
Because it's literally a quartz crystal on the motherboard that vibrates millions or billions of times a second when electricity hits it.
Yes, the system clock.
So a 3 gigahertz processor means that quartz crystal is pulsing 3 billion times a second, dictating exactly how fast the chef's knife hits the cutting board.
That analogy holds up perfectly, especially when you introduce word size into it.
How does word size fit in?
Well, if you have a chef chopping 3 billion times a second, but they're working on a tiny cocktail napkin of a cutting board, the overall output is still incredibly low.
Right, because they can only fit like 1 carrot under the knife at a time.
Exactly. Word size is the physical capacity of the data pathway, so the width of the cutting board.
Ah, okay. So a 32-bit processor can handle 32 bits of data in a single clock cycle.
Right. It literally has 32 physical pins or pathways to move that data.
But modern computing requires a 64-bit architecture now, right?
It does. And that transition to 64-bit wasn't just about moving slightly more data. It fundamentally changed how much memory the computer could even comprehend.
Wait, really? How does the cutting board size affect memory?
Because a 32-bit processor can mathematically only address about 4 gigabytes of RAM.
Wow, only 4.
Yeah. Even if you install 16 gigabytes of memory on the motherboard, a 32-bit CPU physically cannot see it. It doesn't have the addresses for it.
That's crazy. So upgrading the word size to 64-bit expanded that cutting board exponentially, allowing the CPU to address virtually limitless amounts of memory.
Exactly. And then you add in the core count, which is putting multiple independent processing units on a single chip.
So that would be like dropping 4 chefs into that same kitchen.
Right. 4 chefs all chopping on massive cutting boards simultaneously, perfectly synchronized to that one quartz crystal's pulse.
Man, that's a busy kitchen. But so if we have 4 chefs chopping billions of times a second, they're going to run out of ingredients instantly.
Instantly, yes.
The UCM has to have a way to feed the CPU data at just an incomprehensible rate. And I guess this is where the hierarchy of computer memory comes in.
It is, and that whole hierarchy is entirely based on a trade-off between physical proximity to the CPU and the cost of the hardware.
Okay, so the most well-known layer of that hierarchy is RAM. right?
Yeah.
Random access memory.
Yep. And most modern systems use synchronous dynamic RAM, or SDRAM.
What does the synchronous part mean?
It's vital because it means the memory modules actually lock their internal timing to the exact same quartz crystal pulse that the CPU is using.
Oh, so everyone is on the same beat.
Exactly. It ensures the data arrives at the exact millisecond the processor expects it.
But RAM has a massive vulnerability, doesn't it? It's volatile memory.
Very volatile.
And it's volatile because of how it physically stores the data using these microscopic capacitors.
Yeah.
Like those capacitors hold an electrical charge to represent a 1, and they drain the charge to represent a 0.
Right. Basic binary.
But they leak. Right. They constantly lose their charge, meaning the motherboard has to send a refresh signal thousands of times a second just to keep the data alive.
Which is pretty intense when you think about it.
Yeah, because the millisecond you cut power to the machine, the capacitors drain, and every single thing stored in RAM vanishes permanently.
Which is exactly why you have to save your documents to a non-volatile hard drive.
Oh, that makes total sense.
Right. But even with SDRAM syncing to the system clock, it's still physically located, a few inches away from the CPU on the motherboard.
And a few inches is a problem.
At billions of cycles a second. Yes.
Yeah.
The time it takes an electrical signal to travel 2 inches down a copper trace is actually too slow. Yeah, the CPU ends up sitting idle, just waiting for the RAM to deliver the data.
Okay, here's where it gets really interesting. Because engineers solved that physical distance problem by inventing cache memory.
Yes. Cache is amazing.
Instead of putting the memory on a separate stick down the board, they laser etched a tiny amount of super high-speed memory directly onto the CPU die itself.
Right on the chip.
So if RAM is the kitchen pantry across the room, cache is like a small ingredient tray bolted directly to the chef's cutting board.
That's a perfect way to visualize it.
And the CPU checks the cache first. If the data is there, it processes it instantly without ever waiting on the motherboard's pathways.
Right. And then on the completely opposite side of that speed spectrum, you have virtual memory.
Right, which is a fail-safe built into the operating system. Like when you open 50 browser tabs and run out of physical RAM, the OS doesn't just crash anymore.
Thankfully.
Yeah, it carves out a chunk of your permanent hard drive and tricks the CPU into thinking is RAM. It just starts temporarily parking data there.
It does.
But I've always wondered about the logic there. Because if virtual memory allows the system to just commandeer, this massive terabyte hard drive to act as extra RAM, why do people spend hundreds of dollars upgrading their actual physical RAM sticks?
Well, what's fascinating here is the sheer physics of storage mediums.
Okay.
Hard drives, especially the magnetic disk drives that were common when this textbook was published, but honestly, even modern solid-state drives, they're designed for permanence and capacity.
Right, holding lots of stuff forever.
Exactly, not for nanosecond retrieval speeds. So relying on virtual memory is actually catastrophic for performance.
Really?
Yeah. Going back to your chef analogy, if the chef runs out of pantry space, they have to put down the knife, walk out the back door of the kitchen, drive 3 miles to a warehouse, find a single carrot, drive back, and put it on the cutting board.
Oh, wow. And doing that billions of times a second would bring the entire system to a crawl.
Exactly. The computer starts spending like 90% of its processing power just ferrying data back and forth from the hard drive.
There's a term for that, right?
Yeah, it's a condition known as thrashing.
Thrashing. That sounds destructive.
It completely bottlenecks the universal computer model. You have this brilliant, high-speed 64-bit CPU just sitting there doing absolutely nothing while it waits for a mechanical hard drive to spin a platter and find a file.
It really proves that every single component must be balanced.
Everything has to work together.
And that concept of balance and compatibility, it extends far beyond just the inside of a single computer case. It governs the entire ecosystem of devices we interact with.
Oh, definitely.
I mean, the sources cover a massive spectrum, from embedded microcontrollers and handheld devices all the way up to massive mainframes used for corporate data processing.
But they all obey the same rigid rules of compatibility between that hardware layer and software layer.
Right. And the syllabus actually highlights a pretty brutal example of this for Apple users taking the course.
Ah, yes. The great platform divide.
Yeah, because the entire CIS41 curriculum revolves around Microsoft Office 2013.
Right. And for the most part, a student using a Mac can get by, They can install the Mac versions of Word, Excel, and PowerPoint.
The hardware is different, but Microsoft wrote software translators for both operating systems.
Exactly. Until they hit Class Exercise 3A.
Oh, Exercise 3A.
Yeah. This assignment requires students to build a relational database. And there is no version of Microsoft Access for Mac.
It just doesn't exist natively.
Right. The underlying file system and registry architecture of the Mac operating system is so fundamentally different from Windows that porting a complex relational database engine over just wasn't feasible for Microsoft.
Wow. So the literalism of the machine strikes again.
It really does. The instructor actually has to provide an alternate assignment, just a research report on database terms, specifically for Mac users, because they are physically locked out of the software required to actually build one.
It's wild because we tend to view modern computing as this omnipotent cloud, right? Where everything just works everywhere.
We really do.
We rely so heavily on cloud computing, taking for granted that we can save a file to a remote server like SkyDrive, which was the predecessor to OneDrive, and just pull it down on any device.
Right, we expect it to be seamless.
Yet something as simple as choosing a different metal rectangle at the electronics store can entirely dictate what you're capable of doing in a college class.
And this raises an important question about how aware we actually are of the systems we rely on every day.
Like how much we're just ignoring the hardware.
Yeah. The textbook authors even include a disclaimer in their preface noting their book was tested specifically on screens with a resolution of 1366 by 768 pixels.
Which seems so strangely specific.
It does. They go so far as to warn students that if they are running Windows 7, their system dialog boxes will appear light blue, while Windows 8 users will see medium blue.
It sounds absurdly specific to warn someone about the shade of blue on a pop-up window.
It sounds crazy, but it underscores a really vital reality. Our entire perception of the digital world is a highly curated illusion. It's dictated entirely by the specific combination of hardware, firmware, and software we happen to be running in that exact moment. You aren't experiencing the internet, you are experiencing your specific motherboard's interpretation of it.
Wow. Your motherboard's interpretation.
Yeah.
And as we spend more of our lives operating within that interpretation, the syllabus sort of pivots from technical constraints to behavioral ones.
Yes, it introduces the concept of the digital citizen.
Right. Because technological advancements like telecommuting and video conferencing, they dissolve physical boundaries, but they create these really complex new rules of engagement.
The textbooks heavily emphasize the permanence and visibility of digital actions.
Like with copyright, right?
Exactly. They warn students about copyright infringement, specifically the misconception that if a digital image is easily copied, it's just free to use.
Which a lot of people think.
Yeah. The architecture makes copying mathematically flawless, but human laws still govern the action.
And the sources also point out that employers routinely monitor social media accounts and digital footprint.
Oh, constantly.
The network architecture that allows you to seamlessly share a thought with the globe is the exact same architecture an employer uses to track your behavior.
The machine doesn't differentiate between a private joke and a public declaration. It simply routes the data.
Right, it doesn't care. Your actions on these interconnected devices leave indelible traces in databases all over the world.
Which brings us right back to Instructor Lundy's grading rules, honestly.
Oh, so...
Well, operating in a shared digital environment requires the exact same exactness and preparation as submitting a file in his class.
So what does this all mean for you, the learner? We started by looking at a really rigid, unforgiving college syllabus, wondering why an instructor would refuse to accept an assignment just because it had a friendly greeting in the email body.
And by digging through the physical architecture of the universal computer model, the answer becomes pretty obvious.
It really does. The syllabus isn't just a list of rules. It's an emulation of the machine.
Exactly. A 64-bit processor doesn't care about your intentions when you click a mouse. It only executes the binary code it receives.
Right, and a database validation rule doesn't care if you made a typo. It simply rejects the data.
The entire ecosystem of computing, from the quartz crystal dictating clock speed to the capacitors leaking charge in RAM, is built on absolute, uncompromising literalism.
So to successfully navigate that system, you have to format your own behavior to match it. You literally have to learn to communicate on the machine's terms.
Which leaves us with a pretty fascinating concept to consider long after this deep dive ends.
Oh, I like where this is going.
We talked earlier about virtual memory, right? How a computer will simulate RAM using a hard drive to save itself when it gets overwhelmed.
Yeah, avoiding a crash.
And we've seen how a syllabus acts as a programming algorithm, molding human behavior to fit the constraints of the technology.
Right.
Well, today we are offloading more and more of our heavy processing to AI and cloud server farms.
True, everything is in the cloud now.
The intelligence is no longer sitting on the motherboard on our desks. So as those external global systems become the central brains of our daily lives, are we simply becoming the peripheral devices?
Oh, wow.
Are humans just the keyboards and mice, meticulously formatting ourselves to feed clean inputs into a giant planetary universal computer model?
Man, that is a thought that entirely changes the context of every email you type and every file you name.
It really does.
We went looking for the human element in a computer science class, only to find that the machine is actively programming us. Thank you for joining us as we unpack these sources today. Keep questioning the architecture of the systems around you, and as always, keep
Class Exercise 3 is where the margin for error drops to 0. Every instruction in this database assignment is an absolute requirement, and even a minor formatting mistake will cause the automated grading system to reject your file. Before you even open a program, you need to verify your environment. You must have a computer, a web browser, an internet connection, and the correct software suite. As you can see on this textbook cover, the exact software required is Microsoft Office 2013. For this exercise, you must use Microsoft Access 2013. If you are an Apple user, stop right here. Access does not run natively on macOS. Attempting to force a workaround will waste your time and result in an incompatible file. You have two valid options instead. You can either use a PC in a campus student lab, or you can pivot entirely and complete the alternate written assignment, Class Exercise 3A, found on page 19 of your workbook. Getting your hardware and software aligned correctly is the first hurdle of this exercise. It proves you can follow strict operational parameters before you even begin data entry. Start by launching Microsoft Access and selecting a blank desktop database. You are immediately prompted to name your file. The format here is rigid. You must start the file name with CIS41 _. Follow that underscore exactly with the last 6 digits of your student ID, leaving the .accdb file extension intact. Once inside, switch from the default datasheet view to design view. Access will prompt you to save the default table. Name this table Grading in all capital letters and hit Enter. By default, Access creates an ID field with a primary key gold key icon. This automated numbering will corrupt the grading database. On the Design tab's Tool section, click the primary key button to toggle it off. Select that ID row and press Delete. Clearing out that default setting ensures your database remains a blank slate, ready to accept exactly the fields the grading system expects, without any hidden automated conflicts. Now we build the actual structure. You are going to create 7 specific fields, matching the syllabus chart perfectly. Row 1, class, as text. Row 2, section, as number. Row 3, semester, as text. Row 4, year, as number. Row 5, assignments, as text. Row 6, extra, as yes/no. Row 7, points, as number. These 7 rows form the architecture of your table. By defining whether each row accepts text, numbers, or a simple checkbox, you dictate the exact shape the incoming data must take. Data types aren't enough. We need logical barriers, called validation rules, that evaluate incoming data in real time and reject anything falling outside allowed parameters. Click back onto your year row and 2019. This ensures no outdated years can be entered. Select your points row and do the same thing. In its validation rule box, type the less than symbol followed by 31, capping the maximum score. For the section, semester, and assignments fields, you will use the lookup wizard to create lists of predefined choices. This stops typos by forcing the user to select from a specific menu of valid entries. After finishing the lookup wizard, you must manually lock those lists down. With a lookup field selected, go to the Lookup tab. Change the property called Limit to List to Yes. Then change Allow Value List Edits to No. By strictly controlling what can be typed and what can be selected from a menu, you have built a database-ready tool that prevents user error at the source. Your structure is complete, but do not enter any test data. Due to strict storage limitations, any database submitted with actual records inside will be automatically rejected. It must remain totally empty. When you are ready to submit, beware of the open file error. If access is still running in the background, your database is locked. If you try to attach a locked file to an email, the attachment will fail. To safely transport the file, you must completely close the application. Hit the red X in the top corner and shut Microsoft Access down entirely. Log in to the specific course email account you created back in Exercise 1. Open a blank message and address it to the designated assignment email listed in your syllabus. The subject line is heavily formatted. Type your 6-digit student ID, a hyphen, the word database, and an exclamation point. Leave the body of the email completely empty. Attach your closed access file and hit send. The grading system will scan your submission automatically. Watch your inbox closely. If you missed a setting, you will receive an error reply explaining the rejection. Successfully delivering this file bridges the gap between technical database design and professional business compliance. This final step secures your 8 points and proves you can navigate a high-stakes, zero-error environment.